Assalamualaikum. We continue with the discussion about the NMR spectroscopy. In this session, we are going to discuss about C13 NMR. C13 NMR is the second most commonly observed nucleus by NMR spectroscopy. More importantly, C12 is the most abundant natural isotope but has a nuclear spin of 0, so it does not show NMR spectrum. With relate to the C13 nucleus, only 1% of naturally occurring carbon. That's why the signal of C13 is typically 6,000 times weaker than that observed for proton NMR. With the advent of Fourier transform instrument, this is no longer a problem. We can increase the intensity of the signal by take more scans. For example, if 16 scans of 5 to 10 milligram of sample to get a good signal for proton NMR, for carbon 30 NMR, if you want to get a good signal for carbon 13 signal, we have to increase the numbers of scans until 512 scans, so we can get a good C13 spectrum. The position of the C13 NMR also same as a proton NMR, which are affected by the shielding, electronegativity and hybridization, and the position are quite different, which is start from 0 to 220 ppm, and the 0 same, which is the methyl carbon from the TMS. In the C13 NMR spectrum, we can easily identify the presence of quaternary carbons, ipso carbons and carbonyl carbons. This is the chemical shift for the C13. Same as we can compare with the proton NMR, which is the saturated is in the upfield and unsaturated or electronegativity atom will become in the downfield region. Both terms have been used, upfield and downfield, shielded and deshielded. The arrangement in the chemical shift scale also same. Only the scale is different, which is for the carbon 30 NMR, they start with 0, 10, 20 until 220 or more. Here is the general chart for the C13 NMR. If we can see, the specific chemical shift for the carbonyl group is a little bit different between the organic compounds. For example, if ester and carboxylic, the carbonyl carbon is in between 160 to 180, and aldehyde and ketones, it become 190 to 210. In C13 NMR, there are no spin-spin coupling like what happened in the proton NMR with the spin-spin splitting. Why? This is due to the low natural abundance of C13. It is rare to find the C13 in one molecule. Homonuclear coupling of C13 is not observed. The coupling constant are large, typically 100 to 250 Hz. With such spectra observed, they are referred as proton coupled spectra or non-decoupled spectra. If splitting pattern can observe, they just couple with the proton. It's not coupled with the own C, neighboring C. That's the meaning of this sentence. You can see this one, the splitting by the proton for the C13 also follow the rules n plus 1. Let's say if this quaternary carbon means all around this carbon is carbon and no neighboring proton, this signal becomes singlet. If one proton for this carbon follow the n plus rule, it becomes doublet, and this carbon splitting pattern based on the proton around this carbon have 2 proton, the splitting pattern become triplet, and this example around this carbon have 3 proton followed by the rules n plus 1, 3 plus 1 become quartet. The spin splitting of C13 NMR mostly affected by the proton, not by its carbon, neighboring carbon. As we can see, this is a decouple. Means decouple, there are no splitting pattern. And this one is couple. It's a little bit confused for the couple spectrum for C13 NMR, and mostly the researcher run the decouple experiment for C13. This is the example for couple experiment, and this is the experiment for decouple. Means decouple, we are no splitting pattern for each carbon, and each peak only for the one carbon. And this one is couple, means it affected by the splitting of the proton around that carbon. The experiment of decouple is to simplify the C13 spectrum and to increase the intensity. That's why most of researchers prefer to run C13 decouple spectrum. That's all for C13 NMR. Thank you.